With Chapter 5, we're beginning a review of trigonometry and the trigonometric functions. And here's some of the finer points outlined here for what we're going to be discussing with respect to trigonometry in this review. The trigonometric functions, first off, are defined to be periodic functions. What that means is that they are functions designed to describe behavior that repeats over regular periods. A period can be interpreted as a length of time over which a cycle would complete and then start again to repeat the same behavior again. The first topic we'll discuss will be the definitions of the trigonometric functions and associating them with different types of geometries that can describe the trigonometric functions. Those geometries would be circles and triangles. Then we'll talk about the graphs of the trigonometric functions, starting with the sine and the cosine functions, which show up as waves, sinusoidal wave functions, and then also a little bit of discussion of the tangent function as a graph and the reciprocal functions, secant, cosecant, and cotangent. Then we have the topic of identities. And identities are equations which are true, that is the left-hand side and the right-hand side are equal to each other, anytime that both sides are defined. And finally, equations, solving trigonometric equations, solving equations which have, generally speaking, an infinite number of solutions, and we can find those solutions by relating all those solutions to one reference solution, and then using symmetry to define all of the other solutions. Let's dig a little deeper into these topics right here. So periodic function is formally defined to be a function, we'll call it f of t, is equal to f of t plus p, where p is equal to the period, and the period is the smallest value. The smallest value such that this statement is true for all t in the domain of interest. Okay, so this can describe phenomena that in a lot of the natural sciences, for example, describing phenomena that anything that repeats. Some examples could include waves. So waves in a fluid, for example, which also can be associated maybe with the tides in the ocean, which are also associated with celestial periodic patterns, that is, as the moon and the sun. Okay. Their relative position in the sky affects the tides. Electromagnetic waves, so how we perceive light and how we perceive heat, how we perceive electricity and magnetism as well. Also, other things would include, celestial, right? So celestial patterns, sunrise, sunset, lunar patterns, right? Full moon, new moon, those cycles repeat. Seasonal variations. So we could be talking about the seasons of the year, summer to fall to winter to spring back to summer again. It's a repeating pattern, and how we might see migrations of different species of animals. Birds fly south, come back north in the northern hemisphere, for example. Plants, right? The trees, they bloom in the spring, leaves die off in the fall. And then they regrow into spring again. These are repeating patterns, and they are best described by the trigonometric functions. Okay, heart rhythms and blood pressure, regularly repeating cycles, right? Systolic and diastolic pressure readings. Okay, so they vary with respect to time, but they are repeating. Okay, these can all be described again by periodic functions. Okay, anything that is repeating, whereby after some span of time called the period, the smallest span of time where this would be true would be called the period of the function, Okay? If you add that period to any input value of the input variable, the output would be equal to the original value of the function. Those are periodic functions, and they are best described by the trigonometric functions. In the types of geometries which would describe this behavior for us physically so that we can help to visualize this will be within circles and triangles. So we have the trigonometric functions defined in terms of circles. That is, if you can physically imagine a particle or an object that is moving in a circular pattern, so that is rotating. So its position keeps changing with respect to time, but it keeps going around in cycles. So whatever its position is, at some point, let's call this position P0, if it's at its initial position, let's say, eventually, by continuing to move through this circle, I have it right now rotating counterclockwise, eventually it's going to return to this point P0 again, and again, and again, as it continues to orbit. Okay, so this can physically describe, something moving in a pattern which would best be described by a trigonometric function, because trigonometric functions are designed to describe patterns that repeat. Okay. The other geometry primarily that is used are geometry of triangles, and most explicitly right triangles. We can certainly apply trigonometry to non-right triangles, but we'll be defining the trigonometric functions in terms of right triangles, as well as with respect to circles. So in a right triangle, we pick one of the acute angles, and we usually will call it theta, the Greek letter theta, okay, for that angular measure. And again, if rotation or angle is being measured in the counterclockwise direction, we'll be taking the angle or the input value of the variable to be a positive number. If we wanted to switch the direction of the rotation, we could choose a negative number to describe that. So if we choose an acute angle in our right triangle to call theta, then we can label the three sides of the triangle relative to that angle. First off, from the vertex whereby that angle is positioned, if we look outward into the triangle, we would be looking directly towards the side of the triangle we would call the opposite side of our right triangle. And then if we look at the leg of this right triangle, that is, the two shorter sides are called the legs. If we look at the leg that is right next to the angle or attached to the vertex, emanating from the vertex whereby the angle is located, okay, we'll call that side then the adjacent side to the angle. And the third side, only a right triangle has a third side, the longest side, that is called the hypotenuse. So we have those three sides of a right triangle. Where the trigonometric functions can be described here geometrically is if we consider putting this angle into motion, if we were to consider making this angle larger over time, we can examine how the three side lengths of the triangle are going to change, not just independently of each other, but in ratios to each other. So you can just imagine if we were to increase this angle theta, but still have a right triangle, if we were to increase the angle theta, again that is, let's try and visualize that. To increase the angle theta to some other angle, notice that by keeping this a right triangle, we would see that the opposite side is getting longer, for example, right? And maybe the adjacent side is staying constant, but the opposite side is getting longer. Okay, so larger angles are going to be associated with larger opposite sides, is a relationship that geometrically is a useful relationship to describe. The hypotenuse, notice, is also getting longer, okay, but also then the ratios, any ratio of two sides of the right triangle that we might want to examine is going to change, okay, is going to vary as we choose different values of theta. The link between these two geometries, okay, can be found if we were to plot, let's say, plot the circle relative to its center. Okay. And then if we were to consider if the initial side is always pointing towards this point right here, which would lie along the positive x-axis. If we were to rotate in the positive direction, that would be counterclockwise. By the time we reach some terminal point, Okay, we could always construct a right triangle. Right? We can take the point, any point at which we stop at on the circle where we freeze the motion of this particle, let's say, we can create a right triangle in general with respect to the x-axis, and then we can examine the geometry of that right triangle. Now notice that eventually, by the time we get to a point like on the y-axis, we won't be able to construct a complete right triangle. We'll just have a straight line segment up and down. But once we pass into the next quadrant, this would be quadrant 2, at another point that we might freeze it at in quadrant 2, we can again create a right triangle. And notice we'll be able to exploit different types of symmetries that we see here, like reflective symmetries about the y-axis, reflective symmetries about the x-axis as well. Okay. There's a link between right triangles and circles. And that link is going to be described by using the Pythagorean theorem. Okay, the link between these two geometries. The link is by the Pythagorean theorem. All right, the Pythagorean theorem is a squared plus b squared is equal to c squared, where a and b are the lengths of the legs of our right triangle, and c is the length of the hypotenuse. So we'll be defining the trigonometric functions in context of circles and triangles. Graphs of the trigonometric functions. Again, we have the sine waves and the cosine waves. If you can imagine a wave, okay, it has peaks and valleys, crests and troughs. Okay, we have each of these waves has a crest that's at a maximum and has a trough that's at a minimum. Okay, so we find maximums at the crest, we find minimums at the trough. And imagine some object that is moving along this wave, up and down and up and down and up and down. If we were to examine this cycle, if we start from the central balance, call this equilibrium, so we have a crest as the maximum, right? The trough is the location of the minimum, and the balance in the center is the equilibrium. Okay, if we were to start measuring this behavior, which is repeating, right, from equilibrium as we move up towards the crest, and then continue all the way around until we get back to equilibrium, where again we are moving up towards crest again. So if we were to look at this complete cycle right here, which then gets repeated again and again and again, that cycle right there, starting in equilibrium and going up towards the crest first and returning to equilibrium again, just like this, that cycle right there is defined by the sine function. So y equals the sine of x, right, would have an initial wave that looks like this. And then that wave is going to repeat. If that wave were to repeat, right, it would continue outwards and we would get the complete waveform that we see here to the left. Now if we were to examine the exact same wave phenomenon, the exact same one, but start our observation at a crest and then move downwards towards equilibrium until we return back up to a crest again, that is if we were to examine this complete cycle, which I want you to notice is from the exact same wave we were already talking about. It's only a difference of displacement of where we start the initial observation. If we start our observation at a crest until we return to a crest, and we would describe that wave as the cosine function, with the cosine wave function. So y equals the cosine of x, right, be described, its initial cycle is going to be from crest to crest. Okay? And then right, and then that's going to repeat, and that pattern is just going to repeat again and again and again. Right, but in the end, we gather all the same analytical information, whether we were using a cosine to describe this wave or a sine to describe this wave. It's still the same wave overall, so it has all the same information in the signal, whatever it is that we're trying to interpret from the signal. Let's say it was a radio wave and it was carrying information, whether it be speech or whether it be music or something like that, right? Or electromagnetic signal that maybe is carrying some other information embedded in it. Okay. Okay, we need identities in order to be able to define some of the other trigonometric functions as well, not just the sine and the cosine. For instance, we have the tangent function. Okay, and the tangent wave, the tangent wave is going to be one of the 4 other trigonometric functions. Okay, all of those 4 other trigonometric functions have graphs which contain asymptotes. So we're going to be dealing with vertical asymptotes because they're going to have breaks in their domain. So a tangent wave, for example, okay, one initial period of the tangent would look like this if we take a continuous form. And it would have vertical asymptotes at negative pi over 2 and positive pi over 2, and then that pattern is going to repeat. All the trigonometric functions are repeating functions because they are periodic. They all repeat. Okay? And the periodicity is a type of symmetry. If we think of symmetry as a similarity, okay? So periodicity is a type of symmetry. So the identities, right, next major topic for us to discuss in trigonometry or review in trigonometry, would include for instance, reciprocal identities. For example, the secant of x is equal to 1 over the cosine of x. So if we take any one of our trigonometric functions and think of its reciprocal, the reciprocal of any trigonometric function is equal to another trigonometric function. Okay. Ratio, and again, an identity is an equation that is always true. Think of the equation x over x is equal to 1. There you go. X over x is equal to 1. This is an identity. It's a statement which is always true, okay, as long as it is defined. All right? This statement is true when it is defined. For any value of x that you can think of, positive, negative, rational, irrational, okay? With one exception, any value of x that you think of, if you divide it by itself, the output will be 1. So this is a statement that is always true. So when is it not true? Okay? This statement here, x over x equals 1, is not true if x is equal to 0. Okay? So as long as x is not equal to 0, then the statement x over x equals 1 would be true. These are statements that are not meant to be solved. This is not an equation that we are being asked, what are the solutions to this equation? The solutions would be the domain. Wherever this thing is defined, it is going to be true, as opposed to, in general, an equation which might only have one or a finite number of solutions, or even an infinite number of solutions. This has more than an infinite number of solutions. Instead, every value that you can plug in is a solution to an identity. So a statement like secant of x is equal to 1 over cosine of x is true as long as cosine of x does not equal to 0, for example. Anywhere where the cosine of x would equal to 0, the secant of x, its reciprocal, would therefore be undefined, and its graph, the secant of x graph, would therefore have to have vertical asymptotes at those locations. Because these are going to be infinite discontinuities, as we can see, not the removable type of discontinuities. Ratio identities, for example, the tangent function. That is, that the tangent can be expressed as the ratio of 2 other trigonometric functions. The tangent is going to be defined. We're going to see that the way the tangent is defined, it's going to always be equal to the sine of x over the cosine of x. Okay? And another would be the Pythagorean identities. Very important identities as well, fundamentally, in trigonometry. The Pythagorean identities are based off of the Pythagorean theorem. Okay, the primary Pythagorean identity in trigonometry is the one that says cosine squared of t plus the sine squared of t is equal to 1, for example. Okay, and we'll see that that always has to be true by the definitions of the functions sine and cosine. And finally, the last topic for us to review for this course, trigonometric equations. That is the last topic in trigonometry for us to review before moving ahead. Okay, trigonometric equations. So, for example, if you have a trigonometric function, let's say the sine of theta, okay, equal to some quantity, let's say 3/7, okay, then you want to solve that equation for theta. Okay. There will be an infinite, in general, there are going to be an infinite number of solutions. And in order to find those solutions, okay, we're going to use invertibility. That is, we need to define the inverse of these functions so that we can take the inverse of both sides of the equation to cancel the sign and leave theta by itself. But to use invertibility, we need to make these functions one-to-one, required. Take a look back at the graph of the sine function, though. The sine wave is not one-to-one. We know because the horizontal line test, right, would be failed on the sine wave or the cosine wave and the tangent wave. In fact, all 6 of the trigonometric functions, okay, would fail the horizontal line test. But what do we do when we have a function that is not already one-to-one? We restrict the domain. So we're going to restrict the domains of our trigonometric functions in order to build inverse functions, which give us the ability to solve trigonometric equations. Now, the inverse function is going to be one-to-one again. That means when we apply the inverse function, here it would call it the arc sine or the inverse sine. Okay. When we use that function, we are going to get only one answer because it is a function. The output of a function, there can only be one output for the function if the input is in the domain. So, for example, theta would equal the arc sine of 3/7. But that is only one solution to the equation because this is a function. But we know there are an infinite number of solutions to these equations. We can see that graphically. If we were to graph the line y equals 3/7, it would cut right through this wave in an infinite number of points. Okay. So we are going to then have to use different types of symmetry, okay, to find the other solutions, of which there are, again, infinitely many. So we're going to examine different types of symmetries. One of the types of symmetries is periodic symmetry. That if we were to add a period of the sine function to the input, if we were to add a full period to the input theta, we're going to get back to 3/7 again. And other types of symmetries that we're going to use, such as reflective symmetries. If we were to envision this within, let's say, the unit circle or within a circular pattern, we can see that we're going to return to this output value in different quadrants of the graph of our circle. All right, for instance, like the y coordinate of this point right here would also exist over here. We're going to return to that same y value again, but in a different quadrant. So that's a reflective symmetry, okay, that we can exploit in order to find another solution, for instance, to an equation like this. All right, but this would be a basic trigonometric equation, but also more complex looking trigonometric equations, like let's say sine squared of theta plus 3 times the sine of theta minus 5 is equal to 0. This is one that would be, for instance, quadratic in form. So we can use a substitution to express this as a quadratic equation in terms of, let's say, the variable x or whatever, or u or whatever variable we want. We can try to use factoring strategy. Otherwise, we can go to the quadratic formula to see if we can find any real solutions to this, for example. And then once we find individual real solutions, like we did up here, we can then use symmetries in order to find all solutions of an equation like this. All right, and then use of some other identities as well, like the double angle identities, for instance, where you could solve equations like when the sine of 2 theta, let's say, when the sine of 2 theta is equal to the sine of theta, for example, another type of equation whereby we would need to use an identity called a double angle identity or a double angle formula for the sine of 2 theta. Sine of 2 theta is equal to 2 sine theta cosine theta, for example. Okay? And then we can move all the terms to one side, and then we can factor out a sine of theta, set each of the factors equal to 0, right? Use invertibility and symmetries in order to find all the solutions for each of those equations. Right? Those are the main topics for us to discuss within context of trigonometry in this course. And where we're going to start today with discussing the geometry of circles, okay, to get ready for defining the trigonometric functions first within the geometry of a circle. And so let's go to 5.1, section 5.1, titled the unit circle. So the unit circle is defined to have the center at the origin, that's the point 0, 0, and to have a radius, that's the distance from the center to the edge of a circle. The radius is equal to 1 unit of measure. For instance, the radius is equal to 1 foot, 1 meter, 1 astronomical unit, which is the distance from the sun to the earth, for example. If the radius is equal to 1 and the center is 0, 0, we're calling it the unit circle. So here's a graph of the unit circle. It would have points on it like 1, 0, 0, 1, negative 1, 0, 0, negative 1. And the coordinate plane, the xy coordinate plane, is subdivided into 4 quadrants. We have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Quadrant 1 is where the x value and the y value for any point located there, those coordinates are both going to be positive. So we start in quadrant 1, okay, in our rotation. We say in standard position, is when we start a rotation along the circle from the initial point 1, 0. Okay? And if we were to rotate along the circle into quadrant 1, we would say we'd be rotating in the positively oriented direction. Now we're going to define the distance that we traveled along the circle. This is called the arc length, the length of a circular arc. The distance we have traveled from the initial point to a terminal point, that distance in the unit circle is going to be denoted by the variable t. I keep saying distance because I'm not talking about angle here. Not angle. T is the distance we traveled in the unit circle from the initial point to a terminal point. If t is positive, then we're rotating counterclockwise. If t was a negative value, then we would have rotated instead in the clockwise direction. So here's an example where t is greater than 0. And let's say we take a look at an example, how about if t is less than 0? Maybe if we started at the initial point and let's say we rotate it in the clockwise direction to some terminal point. Okay? Then that rotation would be defined where t is then less than 0 because of the direction of travel. But again, t is the distance that we traveled along the rim of the unit circle. For different measures of distance, the coordinates at the terminal point are going to change, right? The position of the object. We're envisioning an object that is rotating, okay, along this circle, and anytime that we freeze the object in its motion, it's going to be at some x-coordinate, y-coordinate position. And our goal with the trigonometric functions would be to relate the distance we traveled along the circle, t, to the coordinates of that terminal point. Right? So that is, we want to relate x to t as a function. We want to define the x-coordinate of this position as a function of the distance we traveled to get there. In the standard position, that is starting from 1, 0 would be standard position. And we want to relate the y-coordinate of our terminal point to the distance that we traveled. We want to design functions whereby the coordinates of our terminal point are related to the distance we traveled to get to that terminal point. And we see that eventually, if we choose a value of t that is large enough, let's say we were to go through an entire rotation and then back again, right? If we choose a value of t that is large enough, we can go through a full cycle and return back to the same point again. Right? That would be then we would refer to that point where we end at as a co-terminal point. That is that there is more than one value of t that we could have selected that would have terminated at the exact same coordinates, the same location. Okay, now this phenomenon is always going to be true in periodic functions by the definition of periodicity. If you were to add a complete period or a full cycle or a complete rotation through this circle, you're going to return back to the same point again every time. Now, what is the measure of the distance around the unit circle? The unit circle, right? Well, first off, a circle in general has a circumference equal to 2 pi r. And circumference is the perimeter or the distance around a circle. But for the unit circle, what is r? R is always equal to 1. Right? That's by definition of a unit circle. So the circumference of the unit circle is equal to 2 pi. Well, all of our trigonometric functions, that is the coordinates at least, the coordinates x and y, okay, are always going to be exactly the same if we were to add a full rotation to t. And if t is always in the unit circle, then a full rotation would be 2 pi. So I'll say right here that the distance I've traveled now would be 2 pi plus the original value of t. All right. So if we were to add 2 pi to the original value of t, we're always going to return back to the exact same point again in the circle. So and 2 pi is the smallest value that you could add to t, such that you would return to exactly the same point. So the period for the coordinates x and y, the period for those functions would be 2 pi. So we could express each of these coordinate functions that exist, and we have yet to give them a name. We are going to give them the name. We'll call them cosine and sine, and that'll be in the next section. But each of these functions which relate the coordinates to some value of t, they each are going to be periodic functions. That is, the x-coordinate for a given value of t is always equal to the x-coordinate of the same value of t plus 2 pi, because if we add one complete cycle, one complete circumference, okay, to the value t, we're always going to return to the same point. And the same for the y-coordinate. Y of t is always going to equal y of t plus 2 pi by this construction. Okay. Now, in general, the arc length, the length along a circular path, in general, is going to be called, it's usually called the variable s. So s would tell us in general what the distance is traveled along a circular path. We would use s if r was not specifically equal to 1. But in the case where r is exactly equal to 1, then we use t for the distance that we've traveled along a circular path. That is the arc length of the unit circle. That's how t is defined with respect to the unit circle. Standard position starts at the point 1, 0. T is positive, counterclockwise. T is negative, clockwise. Now a note on angle. There is a relationship between the central angle of rotation in the circle, okay, a direct relationship between that angle and the distance that we traveled along the circular path. So let's say, for example, that we have the situation whereby we have traveled the distance t from 1, 0 to some terminal point. And if we were to envision that as an observer from the center of the circle, if we were to look outward, we would imagine rotating a ray or an arm towards the positive x-axis initially through a measure of rotation until we are pointing towards the terminal point. And the amount of rotation we have applied, we can call that amount theta for an angular value, an angular measure. There is a relationship between theta and t. The larger that theta is, the larger that t is going to become, right? I mean, if we were to rotate through a larger angle, that would be associated with a larger value of t. And a smaller value of theta would be associated with a smaller value of t. There's a direct relationship. If theta is larger, t is larger. If theta is smaller, t is smaller. If theta is negative, then t will be negative. So, to take care of that relationship so that we can easily convert between discussing an angle versus an arc length, so we have the ability to talk about either, okay? If we choose to define the angle theta by use of the measure radian. Define angle theta in radians, and the radian is specifically defined for this relationship. If the angle is defined in radians, then theta will always be equal to t. That is how the radian is essentially defined. Really, it's defined as technically it's defined that theta is equal to the ratio between the arc length s and the radius r. Right, where s is the circular arc length, okay, of any circle. Okay. But of course, if we are in the unit circle, then what is r? In the unit circle, then r is equal to 1. And in that case, theta would equal s over 1, which is just s. But if we are in the unit circle, instead of using s, we would use t, because t is the arc length specifically in the unit circle. Right? So theta is equal to t by definition of what the radian is, because the radian is actually defined in this way. The radian is defined so that it is equal to the ratio of the circular arc length to the radius of the circle. Okay, and in fact, this equation that relates arc length to angle is only true if we are using radians for the angle. If you were using degrees for the angle, this equation would not be true anymore. It's only true if we use the radian, because this is the definition of the radian here. Okay, so for that reason, that theta is equal to t, we could define our coordinate functions here as functions of theta instead. And they would be exactly the same functions. The difference being, if the input is theta, we're talking about using an angle. But if the input is t, we're talking about using a distance. The periodicity would also be exactly the same. If we increase the rotation by 2 pi, we would have gone through a complete cycle, right? One complete revolution through the circle. So the input variable that we choose is going to determine whether we're defining the functions with respect to distance or angle. And in order for us to be able to easily convert between the two, in the middle of a discussion about distance, we can change the topic to talking about angle. It's most easily done if we choose the angle to be in radians, because that's the way the radians are defined, so that the radian measure of the angle is equal to the distance in the unit circle. Okay? So we're going to have a preference in general for the angles in trigonometry to be measured in radians. Now, that doesn't mean we can't discuss degrees. There certainly are applications for degrees. Okay? But we're more likely to be using the angles measured in radians than degrees by the way the radian is defined. Okay, so we discussed what a terminal point is. Terminal point, that would be the coordinates, xy coordinates of the point where we end on the unit circle. The coterminal points would be 2 points which have exactly the same coordinates, both x and y. Both x and y coordinates are the same. Okay? With different values of the input. It's possible to choose a positive value of t and a negative value of t, which would end at the same point. The reference number is usually going to be notated with either t with a bar, so t bar, or t hat, t with this pointed hat on top. That symbol means that we're using symmetry, reflective symmetries, to refer to a number, okay, a number that represents the distance, because this is t, we're talking about a distance here, the distance in the unit circle back in quadrant 1 that can be associated by symmetry with distances in other quadrants. So for example then, if we arbitrarily choose a distance t, okay, so I'll choose, I'll make a distance t, I'll choose t to be positive for this example. So I'm rotating counterclockwise, and let's say I were to rotate into quadrant 2. Then there is a point right here at the end of our travel. That would be the terminal point. And that terminal point has an x-coordinate and a y-coordinate. Notice that in quadrant 2, the x-coordinate is going to be negative, but the y-coordinate will be positive. Also notice then, by reflective symmetry, that is, if we take this point and reflect it through, in this case, through the y-axis, we would see on the other side of the y-axis, that is back in quadrant 1, by symmetry, reflective symmetry of the circle itself, we would have another point, there we go, another point that is located back in quadrant 1, okay, which is going to have very similar x and y coordinates. In fact, back in quadrant 1, though, in quadrant 1, we would have the absolute value of x, because it would have to have a positive x-coordinate, but the exact same value of y. Right? So they share the same value of y and the same magnitude of the x value, but a different sign in this scenario. Okay? The associated distance that we would have traveled in standard position back in quadrant 1, that distance right there, is the reference number then for our value of t. Again, if t is the distance we traveled from 1, 0, from the initial point to our quadrant 2 point, the green arc, if t is that distance, the green arc's distance, then the reference number t bar is the distance back in quadrant 1 that would have put us at another point that is associated by a reflective symmetry with the actual terminal point. Okay? And notice that the benefit that we get from using this reflective symmetry, this reference number t bar, is that the magnitudes of our coordinates are always going to be the same as the magnitudes of the coordinates of the terminal point. All right, so we notice that these coordinates and these coordinates have the same magnitude as each other, okay? But they differ only in the sign, S-I-G-N, the sign of the coordinates. In this case, from quadrant 2 to quadrant 1, the x-coordinates have a different sign, right? X is negative in quadrant 2, but positive in quadrant 1. But the y value doesn't differ in sign at all. Now let's say we were to take a value of t, I'll even take a negative one. Let's say I take a value of t that puts us into quadrant 4. So I've chosen a negative value of t. That puts us at a terminal point right here in quadrant 4. That point has an x-coordinate and a y-coordinate, certainly. And in quadrant 4, the x-coordinate is positive and the y-coordinate happens to be negative. By a reflective symmetry, this case through the x-axis, there would be a point back in quadrant 1, again, a point back in quadrant 1, such that there would have been a distance, a reference distance. Okay, this is an arrow right here. Okay. A reference distance that we could call t bar here in this magenta color here. This reference distance t bar would be associated with a point here in quadrant 1, which would also have x and y, but now because x and y in quadrant 1 are both positive, right, then we have to take the absolute value of the y. Right, to ensure that both the x and the y coordinates at our reference point are both positive. So again, the magnitude of our reference point here, the magnitudes of the coordinates of the reference point are exactly the same as the magnitudes of the actual terminal point. They differ only potentially in the sign of the coordinates. Okay? By reflective symmetry. If we had a point that were in, a terminal point that were in quadrant 3, notice that a point in quadrant 3 would have an x-coordinate and a y-coordinate which are both negative. We would have to do 2 reflections in order to get back to quadrant 1. We would have to first reflect it through the x-axis and then reflect it through the y-axis. If we would do a reflection and a reflection, either in this direction or a reflection and a reflection in this direction, okay, we would get back to a reference point back in quadrant 1. Okay? And the reference point then, the reference point for this terminal point right here in quadrant 3, we would have to take the absolute value of the x-coordinate and the absolute value of the y-coordinate, because both of them at the terminal point are negative, both those coordinates, and the reference point, being that it will always be in quadrant 1 where we find the reference, has to have positive coordinates therefore. So we can exploit symmetries here, these reflective symmetries, again, so that we can relate any possible terminal point that we could get back to some points that were back in quadrant 1 that would have been associated with a reference number that is always therefore going to be in the interval from 0 to pi over 2. Okay? So we'll note that this reference number that can be denoted either t bar or t hat is always going to be between 0 and pi over 2. Always. So even though t itself, in general, t can be as large as we want, or as large as we want in positive, as small as we want in positive, as large as we want in negative, or as small as we want in negative, right? The reference numbers will always be found back in quadrant 1 between 0 and pi over 2. Okay? Now, if t is a really large number, like say t is equal to 1,000 pi, okay, we can interpret that as the distance we've traveled along the unit circle. The distance is 1,000 pi units of distance. 1,000 pi units of distance. And that can be interpreted as many, many rotations around the circle before we finally come to rest at some terminal point that has to have coordinates x and y. That distance of 1,000 pi can be associated as well to a reference number, right? Which is a number t bar that is again between 0 and pi over 2. No matter how large t is chosen to be, there is always going to be some reference number that by symmetry we can refer to, so that we can easily determine then the magnitudes of the x-coordinate and the y-coordinate. All right, and then we're going to use the information about the actual quadrant of the terminal point to then determine whether our coordinates are positive or negative. But we'll be able to figure out the magnitudes for any value of t by considering the reference number that is associated with it. Now, we are within a quadrant. We are within a quadrant when we are in one of these empty regions these empty 4 regions that are surrounding the axes. It's possible to have values of t that cause us to have a terminal point that is on an axis itself. Every number t will, let's say, terminate at a point, okay, which is either in one of our 4 quadrants or on an axis. If it ends on an axis, we actually would refer to it as quadrantal. So that is, the quadrants themselves do not include the axes. So if you have a point, a terminal point that happens to be, let's say, on the y-axis, let's say that this is our terminal point right here, okay? That would be the point 0, 1, for example. Okay? That point right there is not in any quadrant, for example. It's between quadrant 1 and quadrant 2, but not in either of those two quadrants. We say instead it is on the positive y-axis, and we can also call the input that got us there, we can call it quadrantal. So using these this geometry of the unit circle, let's practice with some exercises. First, find the coordinates of all points on the unit circle such that the x-coordinate is equal to 1/2. First, we can visualize this. There's our unit circle right there. So the point 1, 0 is right here. Okay. X equals 1/2. Okay. Geometrically, that is the vertical line, right? That would graph as a vertical line with the equation x equals 1/2. So that would go through the x-axis at 1/2. And again, is going to be a vertical line. All right, so here is the line with the equation x equals 1/2. And we can see that our line intersects the unit circle in quadrant 1 and quadrant 4. At those 2 points, we want to find the coordinates. We already know the x-coordinate. The x-coordinate at each of these places has to be 1/2. The question is, what is the y-coordinate? I'll call this one y1. So this is the point with coordinates 1/2, y1. And down here in quadrant 4, we have the point with coordinates 1/2, y2. Notice, by symmetry, that the magnitude of y2 is equal to y1. In other words, they have the same magnitude as each other. Now, y1 happens to be positive because y1 is in quadrant 1. But by symmetry alone, the magnitudes of these y-coordinates are the same as each other. Now, how do we find the values of y? One way is we can construct the equation of the unit circle itself. Okay. The unit circle has equation x squared plus y squared is equal to 1. Now, why does that have to be the case from our previous discussion in the course of circles? Remember that the standard form equation of any circle is x minus h quantity squared plus y minus k quantity squared is equal to r squared. That's a direct result of the Pythagorean theorem and the distance formula, the distance between 2 points. Okay. Recall that a circle is defined so that the distance r, okay, is constant. Okay. R is the constant distance from the center hk to any point that we could choose on the circle itself. And the circle is the set of all the points with coordinates x, y. hk doesn't move, but xy does as the object moves through the circle. But no matter what position the point is on the circle, the distance from that point back to the center is always going to equal r. Well, in the unit circle, by definition, we have a center which is 0, 0, so that means h is equal to 0 and k is equal to 0. And r is, of course, equal to 1 unit, right? Because it is the unit circle. So if we plug those into this equation, the standard form equation, x minus 0 squared plus y minus 0 squared is equal to 1 squared. In other words, x squared plus y squared is equal to 1 is the equation of the unit circle. Okay, so now we can interpret the question, find all the points on the unit circle such that x equals 1/2. We can interpret that geometrically as the intersection of the line with the equation x equals 1/2 and the circle with the equation x squared plus y squared is equal to 1. We want to find the intersections. Okay. And how do you find intersections geometrically? By using algebra. Okay. We do so by solving the system of equations. So in this case, we can do a substitution. X equals 1/2. We can plug that into the equation of the unit circle. So we get 1/2 squared plus y squared is equal to 1. And then we can solve for y. There's going to be two solutions. This is quadratic. And we already know from the geometry, as we've discussed above, that we're going to get a positive value of y and a negative value of y. And they're going to have the same magnitude as each other. So I have y squared is equal to 1 minus 1/4, right? 1/2 squared is 1/4. Subtract from 1. 1 minus 1/4 is 3/4. And then we use the square root property. Y equals plus or minus the square root of 3 over 2. So there's our y coordinates. Of course, y1 was the coordinate back in quadrant 1. So y1 was the positive of these two. And y2 was the negative of those two. That would put us in quadrant 4. Okay, so the points of intersection, that is expressing them as points with ordered pairs. We would have in quadrant 1, we have the point 1/2, comma, root 3 over 2. And in quadrant 4, it would be the point with coordinates 1/2, comma, negative root 3 over 2. And that's what we were after. So we interpreted the problem geometrically, both by drawing the unit circle and drawing the line with the equation, x equals 1/2. It was a linear equation, so we can sketch it. And then, again, using geometry, coordinate geometry, the intersection of the line and the circle had to be the solutions we were looking for. And then we went to the algebra, which is if we can describe each of these geometries using equations, which we can. We have the equation of the line and the equation of the circle. We can then form a system of equations between the two and solve the system in order to find the solutions. All right, let's take a look at another example. Find the terminal point determined by t equals pi and t equals 3 pi. And t equals negative pi. Let's take a look at the unit circle. Since we're using t for the distance here, it automatically implies that we should be thinking of the unit circle and its geometry. Okay, so here's our unit circle. Let's interpret geometrically. What does it mean that t is equal to pi? If t is equal to pi, first off, pi is greater than 0. So this would be traveling along the unit circle in the counterclockwise direction, starting at the point 1, 0. Okay. We know that a full rotation, a complete rotation through the unit circle, the complete circumference is 2 pi. And pi is exactly half of that. So we've gone halfway through the unit circle in the positively oriented direction of travel. That is counterclockwise, when t is equal to pi. And that would put us at this point right here. So right now t is equal to pi. That is greater than 0, counterclockwise. Standard position would be starting at the point 1, 0 then, and rotating through the unit circle. Okay, so the terminal point, the terminal point then has the coordinates -1, 0. Now let's take a look at what if t is equal to 3 pi? T is equal to 3 pi. Well, 3 pi is also greater than 0, so we're going to be traveling through the unit circle again in the counterclockwise direction. So we're going to start at 1, 0, and we're going to rotate through a distance of 3 pi. Again, it's going to be that a complete rotation is 2 pi in distance, right? And then we're going to add an additional pi. Okay? And we're traveling actually along the rim of the unit circle. I'm going to offset it on the interior of the circle, but really we're actually traveling along the rim of the unit circle itself. Okay? So we go through a full rotation, and then back again. We're not spiraling outwards, we're actually moving along the circle itself. That's going to leave us off at exactly the same point. -1, 0. Okay. If t is equal to 3 pi, and 3 pi is greater than 0, that's why we went counterclockwise again. Notice we have reached the same point. All right, the exact same coordinates, both x and y. So therefore we have coterminal points for t is equal to pi and for 3 pi. For those different values of t, we are coterminal. We terminate at the same points. All right, now let's take t is equal to negative pi. Well, if t is negative, then we're going to be traveling in the clockwise direction. We're still going to start at the point 1, 0, but now we're going to rotate in the negative direction. All right, so, and the distance we're going to travel, the distance is pi. The negative is the direction, the magnitude of it is the distance. And that would put us going halfway through the circle. That's also going to put us at the point with the coordinates -1, 0. So we get the same point again. So it's coterminal for t equals pi, 3 pi, and negative pi. In fact, there's an infinite amount of values of t that could be chosen which would terminate at the point with coordinates -1, 0. So those are coterminal. Let's return to reference number. Again, that reference number is always going to be in the interval from 0 to pi over 2. There's always going to be some value found along this arc in quadrant 1 where the reference number is never going to be negative, and we can associate it by symmetry to any of the other quadrants, no matter how large t is, whether t is positive or whether t is negative. Now we can use periodicity to take any value of t that is, let's say, larger than 2 pi or less than 0. We can always associate that with some coterminal value of t that would have been between 0 and 2 pi. So say, for example, if we had a value of t that caused us to rotate through a full rotation and then back again, there would be some other coterminal value of t that would have had a measure that is between 0 and 2 pi. So here, in purple here, I would have a value of t that in general is between 0 and 2 pi. And I know since I'm in quadrant 2 here, in fact, this value of t would be between pi over 2 and pi. So this is in general. In general, we can have a value of t, I'll call it t1, between 0 and 2 pi, okay. Whenever we had a value of t here in blue, I'll call it t2, okay, which is, in our case, for instance, greater than 2 pi. Right? These would be coterminal values of t. Okay, and also, if we had some negative value of t, that also would have terminated in the same location. So, for instance, this could be a possibility. It would also be possible to have you would have negative value of t such that we would have gone through also maybe a complete rotation and then back again. Right, and these would have been coterminal as well. Right, so we could have had some t3 would be the orange one that would be less than 0. Okay, and then in yellow, let's call that t4. That would even been less than -2 pi. Okay, so we have t can be negative, t can be very large, or positive more than pi over 2. We can always associate it back to some coterminal point for a value of t that was in the interval from 0 to 2 pi. Okay, that's by periodicity that we can do that. All right, so this, coterminal by the periodicity. And, of course, the period that we're talking about is 2 pi for a full cycle. So we can always get back to some value of t in the interval from 0 to 2 pi. And then, if t is then between 0 and 2 pi, then if we are in quadrant 1 for the associated value of t, that is, let's take a value of t that is now in quadrant 1. Let's get another picture of the unit circle. Okay, so let's put a value of t that is between 0 and 2 pi, but is in quadrant 1. So, for example, this. Notice here that the value of t, then, by this construction, would be exactly equivalent to the value of the reference number. All right? So in other words, if we're in quadrant 1 and t is known to be between 0 and 2 pi, then it must be that t is between 0 and pi over 2 already. So it would be that t is already equal to the reference number. The reference number is already equal to t in that construction. If we're in quadrant 2, where t is between 0 and 2 pi, that would be that t is between pi over 2 and pi, or in the interval from pi over 2 to pi. Okay, so different color, blue. Let's go blue here. All right, so if we have a value of t that pushes us into quadrant 2, so we have a terminal point here in quadrant 2, okay? Then notice that by symmetry, we can associate that back to a quadrant 1 point, okay, such that the value of t in quadrant 1, again by symmetry, that distance back in quadrant 1 must, by reflective symmetry, be equal to this distance right here. That is the remaining distance back to the x-axis. The reference number can always be thought of then as the remaining distance, the positive amount of distance back to the x-axis, whatever is the smallest amount. Well, notice then that then t, the blue distance t, plus the reference number, okay, t bar, has to equal pi. The blue distance plus the remaining green distance, those have to add up to equal pi. As long as we're in quadrant 2, that would have to be true. Solve that for the reference number t bar, then t bar is equal to pi minus t. All right, so if we're given a value of t that puts us in quadrant 2, then that value of t would have to be between pi over 2 and pi. If we subtract that value of t from pi, we would have to be left with the reference number. By symmetry, we can see that that has to be true. Let's go to quadrant 3. Let's go orange. So let's say we have a value of t between 0 and 2 pi, but that puts us into quadrant 3. So at a terminal point like right here, for example. Then the reference number would again be the distance, the shortest distance back to the x-axis. That's the reference number again. Okay. Well, then in that case, by this construction, notice that t, which is more than pi, if we subtract from that the reference number, we would get back to pi. All right? In other words, pi plus the reference number is equal to t. Pi plus the reference number is equal to t. Solve that for the reference number itself. All right? Well, then the reference number then in quadrant 3 would equal t, which is the orange distance, minus pi. And in quadrant 4, let's go purple. If we have a value of t between 0 and 2 pi, that pushes us into quadrant 4. Let's say do this, rotate into quadrant 4. So I'm along this path. So at a point like right here. So we've actually rotated along the rim of the circle until we get to this point right here. in the positive direction because t is between 0 and 2 pi right now. Okay. Then the reference number geometrically is interpreted as the distance back to the x-axis. It's always the smallest distance back to the x-axis is the reference number. So then that means that geometrically we can see that if we take t, then that puts us into quadrant 4, and if we were to add the reference number to that value of t, what would we get? We would have a full circle circumference, which is 2 pi. So in that case then, t bar, the reference number, would equal 2 pi minus t. In all cases, t bar can be interpreted, or t hat, the reference number, is equal to the smallest distance to get back to the x-axis. So now if you're given any value of t, even large positive values or negative values as well, for any value of t, you can relate that value of t to some value of t that was coterminal, that is within the initial period from 0 to 2 pi. Then for any value of t that is between 0 and 2 pi, you can associate it with a quadrant 1 reference number, okay, by symmetry. The reference number will always be equal to the smallest distance along the unit circle back to the x-axis. Let's try some exercises. Find the reference number in the following examples. Find the reference number. A. If t is equal to 4 pi over 3. Alright, so t is equal to 4 pi over 3. We know that 4 pi over 3 is more than pi. 4 pi over 3 is equal to pi plus pi over 3, for example. Okay. How do we know when we're in different quadrants? Okay. Along the positive x-axis, in standard position, t would equal 0 from the start. And then as we rotate through, we know that if we go back to the x-axis again on the negative side of the x-axis, then t would equal t is going to equal pi. All right, if we're traveling in the positive direction, t is equal to pi by the time we get to the negative x-axis. If we were pointing north in the positive y-axis, then t would equal half of pi, or pi over 2. And if we were pointing towards the negative y-axis through an initial rotation, then t is equal to 3 pi over 2. By the time we get back to the positive x-axis again, then t is going to equal 2 pi, and then we're going to repeat the process. For instance, we would be back pointing towards the positive y-axis again at 5 pi over 2. Okay, we would be at the negative x-axis again at 3 pi, right? We would be back at the negative y-axis again when we add 2 pi to 3 pi over 2, okay, which is 7 pi over 2, etc. And in the negative direction as well, right? We'd be at the negative y-axis at negative pi over 2, negative x-axis at negative pi. For example, the positive y-axis, if we're rotating in the clockwise direction again, this would be negative 3 pi over 2. And we'd be back at the positive x-axis again if t is equal to negative 2 pi, and then this would continue. All right, so these are some values of t that would be quadrantal. They would terminate on an axis. Well, we have pi plus pi over 3. That's 4 pi over 3. Let's compare that to 3 pi over 2. Okay. Pi over 3, first of all, pi over 3 is less than pi over 2 because the numerator is constant and the denominator, when there's a larger denominator, we have a smaller fraction. So pi over 3 is less than pi over 2, so that means we know that pi plus pi over 3 then would have to be in quadrant 3. So 4 pi over 3, okay, has to be an element of quadrant 3. Okay, we can conclude that. And in quadrant 3, when we have a number that is between 0 and 2 pi, we can find the reference number, geometrically we can find the reference number as the shortest distance to travel back to the x-axis, and that would be this distance right here in general, for example. And again, formulaically, we know we can calculate that by taking the value of t and subtracting pi when we're in quadrant 3 and we have a value of t between 0 and 2 pi. We can see geometrically that that's what we're going to do as well. So we take 4 pi over 3 and subtract pi, and when we do that, we get pi over 3. So that's the reference number, pi over 3. Okay, so let's try another one. Find the reference number if, let's say, t is equal to negative 7 pi over 6. So let's visualize that. So we have negative pi over 2, negative pi, negative 3 pi over 2, okay, and this is starting at where t is equal to 0. So negative 7 pi over 6 is equal to negative pi minus pi over 6, right? So we are traveling a distance of negative pi, distance of pi, but in the negative direction, and then another pi over 6. Again, pi over 6 in magnitude is less than pi over 2, larger denominator, but the same numerator. So this puts us into quadrant 2, therefore. But remember that we've interpreted geometrically the reference number as the distance back to the x-axis. And t right now is not between 0 and 2 pi. So I'll note right now, right, that although t is in quadrant 2, t is not an element of the interval 0 to 2 pi, because it's not positive. Now we could add 2 pi to t, right, we could add 2 pi to get negative 7 pi over 6 plus 2 pi. With a common denominator of 6, that would be 12 pi over 6, so that's going to give us 5 pi over 6. Okay? And so 5 pi over 6 would be this value of t, 5 pi over 6, right? That would be that value of t as associated with negative 7 pi over 6. Right? They are coterminal. They're both going to end at exactly the same point in quadrant 2, so they would have exactly the same reference number. In either case, what is that reference number? You might be able to figure it out from the geometry right here. Negative 7 pi over 6 is more than, is in magnitude 7 pi over 6. We can see that the distance beyond half a rotation is the reference number. Okay? 7 pi over 6 in magnitude is pi over 6 more than pi, so you might already see what the reference number is pi over 6 in this case. Okay? But we could do a t-bar that we're in quadrant 2 by choosing 5 pi over 6, the coterminal value of t. We could take 5 pi over 6 and we could, formulaically then, we would subtract that from pi. So pi minus 5 pi over 6, and that's equal to pi over 6. So that's our reference number. Okay. So negative 7 pi over 6 has reference number of pi over 6. Interpreted again as the shortest distance back to the x-axis. You draw yourself a picture and calculate that shortest distance back to the x-axis, and you have the reference number. Okay, C. T is equal to 23 pi over 4. So now we have a large value of t. Note, 23 pi over 4 is greater than 2 pi, because with a common denominator, 2 pi would be 8 pi over 4, and 23 is more than 8. Okay? That t is positive, so we are moving in the positive direction. By the time we've gone around one complete rotation, else we would have gotten back to where t is equal to 2 pi. So t is equal to 0 here, t is equal to 2 pi, t is equal to 4 pi, etc., etc. All right. we can subtract instances of 2 pi from this to find a coterminal point. So let's do that. 23 pi over 4 minus 8 pi over 4, that's subtracting 2 pi, a complete rotation, and that would put us at, what would that be, 15 pi over 4, right? And then we can do that again, subtract another rotation, 15 pi over 4, subtract another 8 pi over 4, that'll put us at 7 pi over 4. Now 7 pi over 4 is an element of the interval from 0 to 2 pi, because it's between 0 and 8 pi over 4. So we've subtracted 2 complete cycles, and we've ended at 7 pi over 4. 7 pi over 4 is... Okay. There we go. Now 7 pi over 4 is less than 8 pi over 4, but it's more than 6 pi over 4, and 6 pi over 4 would be 3 pi over 2. So what quadrant does that mean that 7 pi over 4 is in? Well, this is where 3 pi over 2 would be. 7 pi over 4 is going to be here in quadrant 4. Okay? So that's the distance 7 pi over 4 here in quadrant 4. Therefore, the initial angle, 23 pi over 4, right, that would have been found as what? We would have gone through 1, 2 complete rotations and then back again along the rim of the unit circle, and we would have ended at the same point as we would have ended at with 7 pi over 4. So this is if t is equal to 23 pi over 4. Therefore, 23 pi over 4 is found in quadrant 4. And it's coterminal. It's coterminal with the number 7 pi over 4. Now, in quadrant 4, when you have a value of t between 0 and 2 pi, okay, let's use the geometry again, the reference number again, the distance back, the smallest distance back to the x-axis, right? The same reference number for 23 pi over 4 as we would have for 7 pi over 4. Right? It's that distance back along the unit circle. So we can subtract from 2 pi. The reference number then is 2 pi minus 7 pi over 4. And that's going to give us pi over 4. So the reference number is pi over 4. Let's take a look at some of the coordinates of some of the most common points that we would see in trigonometry by use of reference number. If the reference number is in this set 0, pi over 6, pi over 4, pi over 3, or pi over 2, okay, it'll put us at one of the 5 points along the ends of these rays. And the coordinates of those points are listed here in the table as well. So it's important to know these output values as exact values. Okay, they'll show up in their decimal approximations on the calculator, many times. Okay, we want to know these exact values. So we have, if t is equal to 0, for instance, right? If t is equal to 0, we would be at the terminal point 1, 0, because we wouldn't have traveled any distance at all. If t is equal to pi over 6, and that would be this distance right here then that we would have traveled, we would terminate at this point right here, and the coordinates of that point are then root 3 over 2, 1/2. We can justify this geometrically. One way to justify it geometrically is we can construct a right triangle. Referencing this point, we can drop a perpendicular to the x-axis and make a right triangle in here, and then we can go to using theta, which has to equal to t, so theta would equal pi over 6 if we are in radians, and then we can discuss that triangle right there. And when we take a look at right triangle geometry, we can take a closer look at that. Okay, but we can just know right now the coordinates of the point associated with t is equal to pi over 6 would be root 3 over 2, comma, 1/2. If t is equal to pi over 4, that would be the distance along the unit circle to this point then right here. The coordinates of this point would be root 2 over 2, root 2 over 2. Okay. If t is equal to pi over 3, that would be the distance leading to this terminal point right here. The coordinates of that point are 1/2 root 3 over 2. And then finally, if t is equal to pi over 2, that would be if we were to rotate through to this point right here. Right. Then the coordinates would be 0, 1. Now, this pattern here, these patterns, the pattern in the x-coordinates and the y-coordinates, notice we can also relate to each other by a type of symmetry as well. Right? That we have the same numbers in the two patterns. Right? Reading these columns down, the x column and the y column, they're the same numbers but in a reverse order. Right? Now, a helpful way to be able to remember this pattern, let's take just the y-coordinates. The pattern in the y-coordinates. And the pattern in the x-coordinates is just the reverse order of this. Okay, the pattern in the y-coordinates is 0, 1/2, I'll write this vertically. 0, 1/2, root 2 over 2, root 3 over 2, and 1. So here's a way you can remember this pattern. You can express each of these as some quantity first over the denominator of 2. Right? For instance, 0 can be written as 0 over 2. 1/2, well, that's already 1 over 2. Root 2 over 2, well, that's already something over 2. Root 3 over 2, that's already something over 2. And 1 would equal 2 over 2. Now you can write the numerators here each as a square root. That is, in the first case, 0. 0 is the square root of 0. And then take that, divide by 2. 1 over 2, will that be the square root of 1 over 2? Right? Because the square root of 1 is equal to 1. We already have a square root here, square root of 2 over 2. We already have a square root here, square root of 3 over 2. And finally, 2 is equal to the square root of 4. So square root of 4 over 2. So in all cases, the denominator is 2. Right? In all cases, we have a denominator equal to 2. Okay. The pattern in the numerator, right, goes square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. So we can remember that pattern in order to figure out, right, these coordinates. Okay. Now another helpful technique, though, to further try to remember these quantities, let's say if you could look at the fingers on your left hand. Let's pretend that that's my hand. Okay, you're taking a look at your left hand, and if we line up like the thumb with the positive x-axis, and then the index finger along this trajectory, and the middle finger along this one, right, and the ring finger, and then the pinky along here, right? So one finger for each one of these. All right, we can visualize maybe, the object is moving in this direction in the standard position, right? So this would be representing the coordinates 1, 0, for instance, right here. Okay. If you move, let's say, for example, you move through a distance t is equal to pi over 6. The distance t equals pi over 6 would put you at the, right here, at the index finger. Right? It would be at the first finger right next to the thumb. So if you were to fold that finger, close that finger, right? Then notice that you could take a look to see how many fingers there are in this direction, that would be to the right of that are still extended, and how many fingers there still are to the left. Notice that we have exactly 3 fingers that are to the left of this closed finger, but only 1 to the right of this finger. Okay? And notice that the numbers 3 and 1 show up in the coordinates of the point. That is that the x-coordinate, which is read in this direction, right? We read the x-coordinate, we read to the left like that. The x-coordinate is the one that has the 3 in the numerator. The y-coordinate, which would be read in this direction towards the thumb, the y-coordinate has a 1 in the numerator. So I use that interpretation there, okay, to recall that the x-coordinate here, again, the x-coordinate is read this direction from the graph. The x-coordinate is the one with the 3 in the numerator. And we remember the pattern was to take the square root of the numerator's number and divide by 2. We always divide by 2. And the y-coordinate is read in this direction. So we see the number in the y-coordinate direction is 1. So we take the square root of 1 and divide by 2. In other words, the coordinate associated with the number t is equal to pi over 6, the coordinates would be root 3 over 2, 1/2. And this would work for any of these numbers in the list. T is equal to 0, pi over 6, pi over 4, pi over 3, pi over 2. If we associate those 5 numbers, those 5 values of t, with the 5 fingers on our left hand, whereby the thumb is pointing towards the positive x-axis, the value of t tells us which finger to close. All right, let's take a look at one more. Right, so let's say that's our hand. Right, and let's say I now choose t is equal to, let's say, pi over 2. So I'm going to interpret that as the distance from here to here. All right, that's pi over 2. And that's going to indicate on my left hand that I want to close the pinky. So I want to fold the pinky under. Okay, and then we can interpret then from this terminal point right here, we can again read towards the thumb that is back in this direction. We say how many fingers are we crossing over when we read back in that direction? 1, 2, 3, 4. Right? So we have 4 back in that direction. All right? Back towards the thumb is in the y direction. And if we were to read how many fingers do we cross when we look to the left, there's no fingers over there, so we have 0 fingers in that direction. Okay? So then I would say, well, then the coordinates of this terminal point then, right, the coordinates of that terminal point, the x-coordinate, which is read in this direction, right, we read x is read in this direction, y is read in this direction, so the x-coordinate would have a numerator with the square root of 0 in it. Square root of 0 divided by 2. And in the y direction, that's this way, we would have the square root of 4 divided by 2. In other words, the coordinates of the point with where t is equal to pi over 2 would evaluate as 0 for the x-coordinate and 1 for the y-coordinate. So these are the most common reference numbers that you will face in trigonometry, this set of 5. And these are the most common x and y coordinates that you will encounter as well for those reference numbers. And we already took a look at how we can associate these reference numbers to other number values of t that we could get by periodic symmetry and reflective symmetries as well. So let's try an example whereby we can extend upon this idea. State the quadrant and the terminal point for, let's say, t is equal to 4 pi over 3. Now, you might recall we just looked at t equals 4 pi over 3 not that long ago, right, in order to find the reference number for it. We already did this. We said, well, if t is equal to 4 pi over 3, we found that that would terminate in quadrant 3, and the reference number for it was pi over 3. All right, and the reference number was found the shortest distance, the smallest distance back to the x-axis along the unit circle. Okay? Now, if the reference number is pi over 3, remember that that's associated with the coordinates in quadrant 1, What were the coordinates in quadrant 1 for t is equal to pi over 3? If you take a look at your left hand, think which finger is it that you would close if you're given pi over 3. Close that finger and then take a look to the left and to the right. To the left, I'm counting only one finger. So I'm getting the square root of 1 over 2. And to the right, I'm counting 3 fingers. So I'm getting the square root of 3 over 2. So I'm getting the point with coordinates 1/2 root 3 over 2 for the reference. Okay? For the reference number. So if we take pi over 3, then I'm at the point 1/2 root 3 over 2. Now, note that in quadrant 3, x is negative and y is negative. Okay? Then t is equal to 4 pi over 3 is associated with the point with coordinates negative 1/2, negative root 3 over 2. Right, so we found the quadrant, right, by geometrically, right, we found the quadrant, and then we used the reference number and symmetry relative to the quadrant, and knowing the coordinates of the reference number's terminal point, knowing the x and y coordinates, okay, for the reference number from that list above, the symmetry told us which of these coordinates were positive and which were negative, and in quadrant 3, both of them would be negative, and that's how we found the coordinates for our terminal point when given a distance on the unit circle of 4 pi over 3. So we could follow this same process for any other value of t that we are given. Right, we can find the coordinates of the terminal point. Let's try one more. How about if t is equal to negative 7 pi over 6, another number that we looked at recently. So negative 7 pi over 6, that pushed us here into quadrant 2. Okay, same instructions. What's the quadrant and what are the coordinates of the point? Quadrant 2, we want to find out what is x and what is y. In order to find out x and y, we can consider the reference number. Okay, the reference number. And the reference number in this case was pi over 6. It was the distance back to the x-axis. So then we go to quadrant 1, where we have pi over 6, and that pi over 6 is associated with a point that has coordinates x and y, and what would those x and y be? Well, if I use fingers on my left hand, okay, find the finger that would be associated with pi over 6 and close that one. To the left of that, I see 3 fingers, so square root of 3 over 2. To the right, I see only the thumb, so that would be the square root of 1 over 2, or the coordinate 1/2. Now, by symmetry, by reflective symmetry over the y-axis, right, the x-coordinate in quadrant 2 is negative, but the y-coordinate is positive. So we'll take our reference point, root 3 over 2, 1/2, and switch the x-coordinate to negative. So t is equal to negative 7 pi over 6. Then the x-coordinate will be negative root 3 over 2, and the y-coordinate will be positive 1/2. Okay, that completes our reintroduction to the trigonometric functions. To trigonometry. All right, this is the underlying geometry using circles that we'll need for creating the trigonometric functions. In the next section, we'll be defining the trigonometric functions themselves with respect to this geometry here. So try out the homework. Let me know if you have any questions. Feel free to contact the tutoring center as well, right, for extra practice and extra questions. Okay, take care.